Enthalpy of formation. The standard enthalpy of formation has this symbol right here. And right here we tell you how to pronounce it. DeltaH Formation naught. It is defined as the change in enthalpy that accompanies the formation of 1 mole, very critical here, of a compound from its elements with all substances in their standard states. This is another way to calculate the change in enthalpy by using published heat of formation values for the reactants and the products. The degree symbol indicates that a process has been carried out under standard state conditions. We're going to define that shortly. And once again, this is how you pronounce that, DeltaH Formation naught. Thermodynamic functions often depend on concentration or pressure, so we define standard state conditions to properly compare thermodynamic values. Here they are for a compound. Standard state for a gas, 1 atmosphere. For a pure liquid or solid, standard state is the liquid or solid. For a substance in a solution, the standard state is 1 mole per liter. Standard temperature is 25 degrees Celsius or 298 Kelvin. Standard state condition for an element. Only one. That's the form in which the element exists at 1 atmosphere and 25 degrees Celsius. For example, standard state for hydrogen is a gas, and for sodium is a solid, both at 1 atmosphere and 25 degrees Celsius. All elements in their standard state, for example, nitrogen, aluminum, bromine, and calcium, have an enthalpy of formation of 0. It does not take a reaction to create them. When using standard enthalpies of formation, we need to write the equation so that we have 1 mole of product formed, the product is in its standard state, all elements are in their standard state, and all gases are in their standard states. Consider the following 2 reactions. We have nitrogen plus oxygen yielding nitrogen dioxide. Don't worry about this. I'm going to explain that in a second. Normally you don't put a fraction in front of an element, right? We have a DeltaH formation naught of 34 kilojoules per mole. Here we have hydrogen plus oxygen yields water, and again there's that half. And we have a DeltaH formation naught of negative 285.8 kilojoules per mole. In both cases, the gaseous reactants as well as the products are in their standard states at 1 atmosphere and 25 degrees Celsius. Here's the key. 1 mole of product is formed, so you need to have a 1 in front of both the nitrogen dioxide and the water. So let's look at that top reaction. Normally that would be written like this. And we have 2O2, and that would yield 2 NO2. And does that balance? Yep, 4 oxygens, 2 nitrogens. That's how we normally write it. But using standard enthalpies of formation, we need 1 mole of product, so we have to cut this in half. And that's where you get the half. You cut the 2 in half and you get a 1. Here's a sample table of standard enthalpies of formation. The importance of a table like this is that standard enthalpy changes for many reactions can be calculated from these tables, and you're not expected to memorize this. The standard enthalpy change for a reaction is calculated by subtracting the enthalpies of formation of the reactants from the enthalpies of formation of the products. So here's DeltaH reaction naught. It's equal to the products minus the reactants. Sigma still means take the sum. Hopefully you've seen that before in your science courses. The expression means that the standard enthalpy change of a reaction is the sum of the enthalpies of the formation of the products minus the sum of the enthalpies of formation of the reactants. N sub P and N sub R represent the number of moles of each product and reactant. Here's the procedure for calculating enthalpy changes for reactions. First, find the enthalpy change of formation, DeltaH formation naught, for each of the products. Multiply them by the number of moles present and add them together. So that's for the products. Then do the same thing for the reactants, and that's step 2. Subtract step 2 from step 1 to find the enthalpy change of the reaction delta H reaction naught. Calculate the standard enthalpy change for the combustion of methane. Methane plus oxygen yields carbon dioxide plus water. Here's DeltaH formation naught for the various compounds. We write our equation to find delta-H reaction naught. Note it's the products minus the reactants. So let's look at the first one. Here's a product, CO2. There's 1 mole of CO2. And where is its delta-H formation naught? Let's see, that's minus 394 kilojoules per mole. Good. Then we have 2 moles of water, liquid. And that's minus 286. So there's the minus 286. There's the 2 moles. Now we subtract the reactants, and we have 1 mole of methane. Here we go, and methane is negative 75 kilojoules. And then we have 2 moles of oxygen, and the oxygen molecule is 0 kilojoules, is delta HF naught. Do all the adding and subtracting, and we get the delta H reaction naught of negative 891 kilojoules. Calculate the standard enthalpy change for this reaction. We have aluminum plus iron oxide yields aluminum oxide plus iron. We have our equation for the standard enthalpy change for this reaction, and we'll be subtracting the reactants from the products. So let's look at the products. We have 1 mole of aluminum oxide, and that's minus 16.76 kilojoules per mole. Then we have 2 moles of iron, and that's over here, and we have 0 kilojoules per mole. That's delta HF naught for the element. We subtract the reactants. So aluminum, again, it's a pure element there, 0 kilojoules per mole. And here's the iron oxide. Do the math, and we get delta H reaction naught is negative 850 kilojoules.